that if you remember, okay. Yeah, let me say that and it's okay. So there was this alpha term, like this was, so you're looking at alpha NV freeness in the previous talk.
Yeah.
And you had this alpha. I don't want to change slides, but I can like.
That's okay. We can talk about it later also.
No, I'm just saying like.
No, like I remember what you said about
That's
the approximation factor for the NV fields, right?
Exactly. Yeah. So what we had was this alpha times Ka, and it was a geometric mean. But imagine a setting where I actually have like alpha A Ka. So this alpha is varying with agents. So for some agents, it's like really good. It's half NV free. It's almost one NV. For others, it's worse. So, if you look at the factor, it's actually the geometric mean of those. It's geometric mean of alpha Ka.
Right. Okay.
Somehow, if you can balance that for agents for whom Ka is large, you really have good. Which, I mean, if you stare at the algorithm, it actually does it. Like if you're getting it's sort of a cliched sentence, but you have more NV when your values are high. Like the interval growing algorithm has this flavor. So
really?
that sort of points me that okay, there might be some, at least for the approximation, there should be something
interesting
right here. So though it is APX hard, Nash welfare in cake division.
Sure.
So it's not like you can get a PTAS or something, but nonetheless, I do think there's scope there. Yeah. The egalitarian one is like much more mysterious, like the huge gap.
You mentioned that, yeah.
Yeah. So
these hardness results, are they also for the connected case, or they are for the non-contiguous allocation?
No, they are for the connected. Like non-contiguous, I think this like you break it up into small value pieces, and then like I think it's almost greedy, for example. Like you can do it now. Egalitarian still is hard because
right.
Yeah. But yeah, I do think like a lot more. Like life is much easier then.
Okay.
Yeah. So there's this recent like ongoing work with Pooja that gets like a additive. So this in the paper I presented, the additive approximation is one third NV free additive.
Yeah.
So you can improve that to 1/4 for all.
You mentioned that, right?
Yeah. So and yeah, there are like I think at least we are hoping that there are some ideas that will push it to a bit more, but yeah. Yeah, it's two. Let's start, I guess.
Should you start, Sushmita? Is this a good thing?
Yes, let's start.
Okay, cool. Yeah, so welcome back for the afternoon session. And Siddharth Burman at ISC is going to continue his talk on welfare maximization in the context of right division. Yeah, please go ahead, Siddharth.
Excellent. Yeah, thanks everyone for participating on a Saturday afternoon. I'll continue talking about collective welfare and like just to spend a few slides recollecting what the background we did last time. So this is sort of the overarching theme of our pursuits. Like we are looking at these class of objective functions, class of welfare functions called generalized means. They have this general expression like this. So for different values of P, I get different instantiations of this welfare function. And so they are not only like a natural and algorithmically interesting class of functions, they come with a axiomatic backing. So they're fairness axioms, starting with which you can show that these are the class of welfare functions, objective functions that satisfy those fairness axioms. So in the context of dividing goods, dividing resources in a fair manner, these are a natural class. They're not just natural, they're an axiomatically important class of functions to study. And this is what we'll do. We will look at different contexts, different settings, and try to maximize these P welfare functions. And three important members of this family are the utilitarian welfare, the social welfare, which is obtained by setting P equal to 1. So when P equals 1, this reduces to the arithmetic mean. And P tends to 0, again, this is a simple exercise that this expression reduces to the geometric mean, and this is called the Nash social welfare. When P tends to -infinity, I get a purely fairness criterion called the egalitarian welfare or the Rawlsian welfare. So this expression is interesting for us when P is less than or equal to 1. And again, just to recall that Nash social welfare actually achieves a balance between the extremes of fairness and allocative or assignment efficiency. So this is an important member in this class, in the especially in the context of fair division, or welfare with fairness guarantees is important. So throughout the subscripts, it denote the value that the agents will accrue through various divisions, various partitions, and so on. So that's the overarching objective function. We also saw a list of applications. I'll not go through them again. There's this popular website, splitit.org. You can go and check it out as well. What these applications kind of led us to was this very simple taxonomy over the settings you would like to consider. So and the taxonomy was simply based on looking at the goods that we are dividing among the n agents, the sort of the resource that we are dividing, and the good could be divisible or indivisible. So divisible would include things like food, land, water. Indivisible, the examples we saw were courses and housing units. Divisible, it could be heterogeneous, like land, of course, different areas, the same, say, square footage of land or same stretch of land has much higher value in certain areas compared to others. And this is referred to as cake division, the heterogeneous cake. And we kind of saw this result on maximizing Nash social welfare in this heterogeneous divisible goods case. So we did cake division last time, and today we'll do food division. And so this is what you get when you give me a post-lunch slot. These are the kind of things I'll start dividing. So food division will fall under this umbrella of homogeneous divisible good. Like if you have 10 kgs of grain and you get 1/3 of that, your value is 1/3 of the total 10 kg batch. So that falls under this leaf here, homogeneous divisible good. And at the end, I'll mention results about indivisible goods case. This is unlike this part of the subtree, which is sort of has a continuous optimization flavor to it. This is completely combinatorial. It's a partitioning problem here versus a fractional assignment problem on the left-hand side. Some sense, this discrete indivisible case is the most active area of research in the past, let's say 4 or 5 years. Dozens and dozens of work, lots of nice techniques, heavy hammers like real stable polynomials, and using, for example, Fisher markets in the service of algorithm design. So yeah, lots of interesting connections, lots of, in fact, open problems in this space. So at the end, I'll point to you to 2 surveys that talk about discrete fair division, so fair division of indivisible goods. And these 2 surveys have come out in fact, less than a month ago. So these are like fresh off the press surveys with many interesting open problems. So yeah, if you're interested, this is a great area to sort of explore. Right, so this was last time, Nash welfare for cake division. Today I'll talk about homogeneous goods, and then the third part of the talk would cover indivisible goods. So yeah, let me move on to homogeneous. And the problem I'll study would be an online problem. I'll set up the model and describe it in bit detail, but roughly speaking, what's going to happen is that will sort of receive these goods that are divisible, and so I can fractionally assign them among the agents. The value of the agent would depend on the fraction that she receives. The challenging aspect would be that this needs to be done online. I'll give you a very nice motivating application to sort of that sets up this model or sort of substantiate the relevance of this online setting. And this is joint work with Arindam Khan, who spoke earlier in the workshop, and our very prolific intern Arnab. So this very recent work, kind of quite excited about this. So homogeneous divisible goods in an online setting. So here's sort of the mathematical or the formal setting. I will have agents again, 1 through n as before. And for each agent I and each good G, what we'll have to do, the decision that needs to be made is to figure out a fractional assignment, right? So unlike the cake where there was just one cake and I was giving subintervals, now I have many goods, say M goods. And for each good G, and for each agent I have to decide what fraction of this good G goes to this agent I. So this is the decision variable xgi. It's a number between 0 and 1. So that's the fraction of the good G that goes to agent I. And when it's summed across all the agents, so fix a good G, sum it across xi's across I, that should be 1. So you have to take the good and like divide it fractionally among the agents. And the valuation is just simply additive. That is, each agent I has a number, has a value for this good G, that is this VIG right here. The total value that agent acquires by getting different fractions of different goods is just this sum, right? So here VGI is a given number. It's a fixed number. That's the value that an agent I has for a good. These are the decision variables, XGIs. What is the total value that the agent gets at the end once you have made these fractional assignments across all goods? It's just the sum. So it's additive valuation, divisible, homogeneous good. Okay. And fine, like if it was an offline problem, that is, if I told you all these VGIs for all the agents and all the goods, these VGIs upfront, you can go and just write a concave optimization problem. In particular, these are the number of agents times the number of goods, decision variables. Look at this expression, maximize it. It's a continuous optimization problem. The objective is concave. Fine, you can find the optimal. So nothing sort of grand about it. What I'll do now is move on to an online setting where the problem really becomes interesting. And I am going to assume a normalization, and without which non-trivial results cannot be obtained, at least in the case of an adaptive adversary or a powerful adversary. And that normalization, I'm going to assume that for every agent I, so fix any agent I, if I look at the value for the grand bundle, so the value for all the goods, so summing over all the goods G, this total value is normalized to 1. So 1 is just a scaling thing. It doesn't have to be 1, but these values just sum up to 1. And we are in the goods case. So these are non-zero, non-negative, but yeah, this is the scaling assumption. I'm going to assume it's not going to be very apparent why I need it. I'll tell you one place where it is required, but yeah, like what I'm not going to spell out is like, if you don't have this, then you can't do much. Like pretty much in the online case, you're kind of going to get only very trivial guarantees. Okay. So as I said, this is a fairly well-motivated problem. And let me recall one of the applications that I mentioned earlier. This is work by Alexandra et al. This was done with Food Bank Australia. This is sort of a nice study where what they do is they like sort of look at the problem of so you have a hub, it gets food donations every day, and you have to distribute this food across different soup kitchens, across different, say, canteens. And you want to do it fairly. So the resource that's being divided are the food donations for every single day. So G here is going to be the food batch for every day. So every day you have and when the food arrives, it's only then, and it's only on that day that you know what the values are. So different soup kitchens sort of report their value, which you can think of it as like, this is the demand they have on that day. So food is a divisible resource. This is indeed an online problem. You cannot just store the food for, let's say, a month and then say, oh, you know what, just stay hungry for a month. At the end, I'll solve a nice concave optimization problem and give you a very optimal solution. That's not a luxury we have. This food allocation problem is also studied by other groups, in particular group at Cornell, Banerjee et al. Also look at this. They solve, in fact, this specific optimization problem for the Nash social welfare. So they have an intricate primal dual schema for exactly this optimization problem in this online setting. And they obtain competitive ratio guarantees, which I'll sort of compare with ours later. They're slightly better, but I mean, the punchline is that ours will work for all mean welfare, whereas they focus on Nash social welfare. Also, like, yeah, just to be fair, their results are slightly more robust. They work in this paradigm called algorithm design with predictions. So extending our work to that is also an interesting thread. But yeah, long and short, this food bank problem is going to motivate this online study. And let me just spend one more minute and like spell out the connection. So what are the agents here in this fair division exercise? These are the soup kitchens, the canteens. So n, small n, the number of agents in this picture, for example, is 3. I have to divide food among these 3 soup kitchens. And what are the goods? And these are the food donations you receive every day. So at the hub, at the central hub, food comes in. This is the good, the first good. And the decision you make are these XIJs. So this is the XIJs for the first good across. So you point like 20% of the good goes to the first canteen, 30% to the second, and 50% to the third. Say on the first day, a lot of people showed up on the third canteen, you would want to distribute it like this. The point is that when the good shows up, the canteens, i.e. the agents report their value, you then decide these XIJs, and these are irrevocable decisions. Like once you have given them, the food is consumed, you're done, and you can't wait. So these have to be done online. You have to make these decisions as and when the day progresses. So this is on day 2, things starts afresh, another batch, another set of values reported by the agents, the canteens. You make another decision for these XGIs now for the second good, so on and so forth. And when at the end, like let's say at the end of the month or whatever stipulated window, you look at this value acquired by all the agents, and your overarching goal is to sort of find these numbers, XIJs, such that this function is maximized for whatever P you want. And we've discussed this at length, that this is a good welfare metric to study. For example, Nash is a good welfare metric to study in this context. It's a good, fair way of, axiomatically justified, fair way of making decisions. So that's a not just a natural objective, but a well-founded one in this fair division exercise. Okay, that's the setup. I will now kind of jump to the algorithm. So just make a mental note of what we are doing. And very surprisingly, and sort of the algorithm is going to be hauntingly similar. I will again, it's a few lines of pseudocode. I'll be able to express the main ideas. There are finer details, and I will not subject you to them. I invite you to read the paper for those nuance points, and there's certain details that I'll gloss over. My purpose is not to sort of subject you to every possible detail in all possible cases. I want you to convey, I want to convey the main idea, the guiding intuition that works here, and the sort of how clean this algorithm template is. So the sort of elegance of it is what I'd rather focus on. I will present the technical ideas, but just roll with the punches. I'll not there'll be points where I'll skip lower order terms and so on. So just, yeah, it's more the intuition and the sort of proof sketch than the exact details. So yeah, here's the algorithm. In fact, it's a 3-line algorithm. What's impressive about it is that this algorithm will work for all values of P. It's a family of algorithm. It's governed by this threshold T. So for different P values, for different P means, I will only change this threshold T, and I'll get the algorithm for that P value, for that generalized mean. And we'll show that for a wide range of P, this single template, this single algorithm design will work to give us essentially tight competitive ratios. So recall from Professor Amit Kumar's talk that in the context of online algorithms, the metric of choice is competitive ratio, which in this case is the optimal P mean welfare when computed, say, offline or at the end of the entire exercise, divided by the P mean welfare. So the optimal by the P mean welfare achieved by the algorithm. So the closer to 1 that ratio is, the better it is. You want that ratio to be small. The competitive ratio, so the analog of approximation ratio in the online world. So here's the algorithm. It works with a threshold tau, And what it does is it maintains two subsets of agents, right? The first is an active set of agents, which are agents who have yet to acquire a value of tau. So let me be specific. As the algorithm progresses, it makes allocation decisions. The next good comes, it fractionally assigns it among the agents. The subsequent good comes, it again fractionally assigns it among the agents, so on and so forth. So as these fractional assignments are happening, the values acquired by the agents keep on increasing, so that the sum of xig, vigs keeps on going, summed over all the goods that have been assigned so far. So what you do is you look at this threshold tau and maintain those agents that have yet to acquire a value of tau, right? So initially, all agents are active because they've only acquired, say, value 0, and say if tau is positive. In that case, all agents will start out to be active. As the value increases for agents that cross this threshold, they have already acquired a value of tau, you sort of kick them out of the active set. You tell them, look, you know what, you have received enough, just be happy, go out. The second set you maintain is a set of vulnerable agents, which is actually a subset of A. So V, by definition, is a subset of A. And these are agents for whom, if you look at the total value of the goods that is left, that happens to be small. I will quantify what I mean by limited value left, but here is where I use the fact that the grand bundle is of value 1. So I look at every agent that is active, so still hasn't received a value of tau, and then I look at the total value that has gone by. So not just the value that this particular agent has acquired, but the total value of the goods, the cumulative value of the goods that have gone by. Subtract one, like this quantity from 1. So that's the value that still remains, right? So I'm saying, okay, here's an active agent. In the future, if I were to give her all the goods that remain, even then that's a small number. So that agent is going to be vulnerable, right? Like it's now in a red flag zone that even if I assign this agent everything that remains, like her value is small. So those I define to be the set of vulnerable agents. Okay, and that is it. Like once I have that and these two sets I can maintain online. The only thing I need is this total value normalization. Once I have that, I can maintain these sets based on what I have seen so far. And here's this online decision, this online irrevocable decision. The good comes in. It's a fractional, like it's a good that's divisible. I take 1/3 of the good and then I uniformly distribute it among all the agents. So this is more of a fail-safe. In the analysis, it won't play like at least in the presentation, it won't make a sort of important dent. This is important. Like when you read the paper, you'll realize that this is a good thing to do as a backup, right? So at least you ensure that every agent gets some bare minimum value. So this is what you do. Let's say you get this 30 kgs of rice, 1/3 of it is 10 kgs. You just divide that 10 kgs uniformly among all the n agents. Fine, so that's gone. Then you look at another 1/3 of the good. So you pick the agent that has the maximum value for it among the active ones. So this A here is important. So you look at agents who are active. Among them, you ask them, okay, what are your values for the good? The one that values it the most, you give it to her. So that's a purely greedy step. A large chunk of the good, 1/3 of it goes to this active agent who has the most value. Another 1/3 thing, you do sort of an egalitarian exercise. So interestingly, at a high level, this is a mix of the two extremes. 1/3 or like some part of it, you're purely being egalitarian, uniformly distributing. The other 1/3, you're just doing a very greedy exercise, giving it to the agent that values it the most. So the 1/3 that remains, you assign it among the vulnerable agents. So that's the algorithm. Yeah, I'm still surprised that this simple, like very clean, direct idea works for such a general class of evaluations. Yeah, analyzing it is a fun exercise, but at least in terms of the design aspect, it's a rather clean thing. let me just make a quick note that if my goal was only social welfare, only like the arithmetic mean, then all I had to do was this step and not even look at greedy, not even look at active set. I could just look at all the agents and every time just greedily give it to the agent that values it the most. So that would maximize social welfare. This is a mix of the whole thing. Okay. All right. So far so good. Any questions? No, I believe. Right.
Yeah, nothing so far.
So here's the, like, before I analyze it for like one case, one particular value of P, here's the set of results we obtain. And this is by no means a single analysis. Every colored interval you see here is a different case. But what we obtain is that as you as you pick tau, the threshold of the algorithm for different values of P, these are the competitive ratios you obtain. Let me parse through this picture. It's sort of the summary of all results, if you will. So if I start at, so this x-axis is this exponent parameter P for the P mean welfare. If I start at minus infinity or a very small, this is egalitarian welfare. For this, what we can show is that for a specific value of tau, the competitive ratio is something like O tilde of square root n. So up to log factors which are being hidden, subsumed in this O tilde notation, competitive ratio is square root n. And one can show that this, in fact, again, up to log factors, this is tight. No online algorithm can achieve better than like square root n, like omega square root n competitive ratio. So this is a tight guarantee. This ends up being tight till, in fact, something like the harmonic mean. So till -1, you have a lower bound and an essentially matching upper bound through this algorithm. Tau, in fact, in this entire range stays the same. So all these phenomena that emerge were not obvious to us a priori. And like, this is quite interesting that, yeah, like you have these competitive ratio, there's this like a sudden threshold phenomena and it drops like the competitive rate. If you look at it, this x-axis is not to scale. This from -1 to minus infinity, you have a relatively high competitive ratio, albeit it's tight. But suddenly from harmonic mean to this term -1 over log n, the competitive ratio drops. And again, you can show that maybe not up to polylog factors, but there are morally matching lower bounds even in this regime. And these are slightly complicated expressions. To analyze the competitive ratio of the algorithm in this range, you have to use like series expansion ideas, tricks from calculus, so on and so forth. So you do get competitive ratios that look, for example, in this range. Again, -1/4 isn't nothing sacrosanct about it, but yeah, for some constant that's say smaller than -1/2 or -1/3, you get a drop like n to the 2, the absolute value of P. So once you get to something like -1 over log n, the P value, you have now dropped. If you plug this in, you have now dropped to a polylog factor. And then it stays that way. So in particular, for Nash social welfare, there is a tau value that I can plug in. There's a threshold that the algorithm can be operated with, and I get a competitive ratio of log cube n. So Banerjee et al. Actually just study this case and show that the upper and lower bound in this case is log n. So we are again log square n off. Yeah, the point, however, is that their algorithm is tailor-made for Nash social welfare, uses like a fairly nice primal dual schema. You do like this algorithms with prediction ideas kind of come in there. But so sort of, again, the fact is that it stays this way. And there are discontinuities here. This, I think, is more because of our analytic limitations rather than a natural limitation of the algorithm. So that's something to sort of look forward to in future work. But yeah, it's kind of stays to log cube n. And as I mentioned earlier, for P equal to 1, it drops to 1. You can do the optimal thing even in an online setting. But yeah, it stays log n up to pretty much up to 1. So that's the sort of entire spectrum of results we obtain through the algorithm. Let me repeat, it's not that there's a singular analysis that ends up working. One has to sort of work through it and like really sweat out the case analysis and do these different regimes properly. however, yeah, the nice thing, the one that I like about this result, it's kind of sort of find it interesting, is that, yeah, a single algorithm, single idea kind of works through for this entire space of valuation function. So that's, yeah, yes.
May I ask a question?
Sure.
So to interpret this fact that there's this sharp, you mentioned that when the slope comes down, there are somewhat matching lower bounds, right?
Yes.
So is it fair to say that the value of tau somewhere between this -1/4 and this -1 by log 2n,
Yeah.
there is a phase transition?
Yeah, I think so. Yeah, it seems like it. So again, yeah, this is not tau. This is the p-value. The
P-value, right? So
yeah.
with respect to p-value, sorry. So with respect to p-value, there's a phase transition. I say this because it's not an art sort of a limitation of your algorithm, because if you have a matching lower bound, then it means that in the online setting, this is the best one can hope to do, right? Isn't that the way the is that the way to interpret the lower bound and your matching upper bound?
Yes, and let me be a bit precise about it. So so the lower bound actually looks like square root n up to log factors till say -1. In fact, you can push it a bit more. So it is quite high. So in this, again, neither the x-axis nor the y-axis or scale, this is more an illustration. This is a large number compared to log n. And suddenly, when p goes from here to, let's say, below, the lower bound also drops to log n. So close to 0. So say in this regime, you have a lower bound of log n. Here, the lower bound is quite high. So there is a drop, and this is not a large range. Like this is like -infinity. So a lot of heavy lifting is being done by this small looking interval. There is a phase transition here, right?
Yeah, because of the comparative length of this portion with that, it just seems like there's a drastic drop. So thank you.
Yes.
Another question in the chat. Should I read out?
Yes. My analysis is tight. So Shivika is asking, is your analysis tight for egalitarian, tight again up to log factor? And let me take credit. Okay, I have a visitor among. Up to log factor, yes. For egalitarian, the analysis is tied to the extent, like not just the analysis. It's there's a lower bound of square root n. We get an upper bound of something like square root n log n or log square n. So there's a log factor being hidden, but up to that and prior to this work, there was no known algorithm even for the egalitarian welfare, let alone for others. So the only known result for this whole x-axis was naively the social welfare and this Nash social welfare. So this egalitarian welfare, even as an algorithmic result in and of itself, is a nice contribution. In fact, that's the proof sketch I'll give you will be for egalitarian. Okay, can I move on? Okay.
Yeah, please. Sorry.
Fine. So here's the quick repetition. That's my algorithm. I have a single set of active agents. The algorithm performs with a given threshold tau. The set of vulnerable agents for whom the total value of all the remaining goods is small. And for each good, I just make 3 decisions: uniform over everyone, greedy in the active set, and uniform over the vulnerable set. That's it. Okay. As I said, like the analysis for different values of P is involved. Nash is slightly simpler, so you can sort of easier to read. But let me give you the key idea, one key idea, and exemplify it by looking at the egalitarian welfare case. So by which I mean, I want to divide the fractional goods such that the minimum value across the agents is as high as possible. So the P equal to -infinity case, I want all agents to have a high value at the end of the fair division exercise, at the end of it, once I've allocated all the goods. Again, to simplify exposition, I'm assuming that I know this optimal upfront, like I know eta star, the optimal egalitarian welfare. Certainly, I don't know the solution. I don't know how each good is divided. All I'm saying is that there is a solution. There is a way to fractionally divide the goods such that every agent gets eta star. How do I deal with this? sort of in the paper, or like because this is an assumption, well, what you can do is like run this algorithm for d-adic scales, like 1 over n, 2 over n, and then from 2 over n to 4 over n and so on. So that's a place where you lose a log n factor. So you just sort of guess where the optimal is and run those copies of the algorithm in parallel. The goods are fractional, so you can do all this. Again, read the paper, talk to me offline. For the time being, let's just roll with me and like imagine that I know this eta star. That is, I know that there is a solution wherein all agents are getting a total value of at least eta star. Fine. For this case, what is the threshold? This is what I do. I set the threshold to be eta star by square root n, the number of agents. When I set the threshold to be that, my definition of the active sets is that these are agents who have received value less than eta star by square root n. So that's my threshold. I'll only keep an agent active till her value hits this threshold. And in this case, the vulnerable set are the agents for whom the total value left is eta star by 2. So that's a really small fraction. In particular, it says that, look, like if you have become vulnerable, and if I give you all the remaining goods, even then you're only going to get eta star by 2. So that's the definition of a vulnerable set. This online decision stays the same. Okay. So that's the algorithm for egalitarian welfare. These are the instantiations. This changes for different p-values. For Nash, this is a more generous threshold and so on. So yeah, we encourage you to read the paper, but once you've seen the presentation, a lot of things would be sort of clearer, like why are certain decisions being made. Okay, as promised yesterday, I will give you proofs that fit in a slide. So yeah, conforming to that, here's the sort of proof sketch of why this works for the case of egalitarian welfare. So the first observation I'm going to make is that if I look at the social welfare acquired by the algorithm, that's actually upper bounded by this expression. Why is that? So let's just ignore the uniform part. That's more a fail-safe. So let's look at the social welfare that's assigned to agents as they are part of the active set. So once you're off the active set, you're not going to participate in this argmax, you're out, and you'll not get any fraction of the good, at least like these two parts, because V is also a subset of A. So what you are getting value, you are acquiring, any agent is acquiring value till she is in the active set, and which means that any agent, the upper bound on that is by this threshold is eta star by square root n. There are n agents, so the total social welfare is at most eta star by square root n. Note that this is an upper bound. I'm saying ignore the uniform part for the ease of exposition or for this presentation. So just look at these two parts, and the total value that's acquired is only when you are active, and this is what it is. Fine, that's an upper bound. Is a next useful observation. So look at an agent, and she is now a part of the vulnerable set, right? So note that if no agent ever becomes vulnerable, you're actually golden. You have ensured that if all the agents stop being active, it means that you have assigned eta star by square root n to everyone, which means that even the algorithm has hit this egalitarian welfare up to a square root n factor in the denominator. So you wanted to give everyone eta star, you have given everyone eta star by square root n, fine. Your competitive ratio is square root n, done. So the only bad case is when you have vulnerable agents. So let's look at one of those. So fix an agent I, she's vulnerable. Now, how has this happened? This has happened only because I has lost, and I'll explain what this means, at least eta star by 2 of her value. So this is slightly a delicate observation, so let me spell it out. What I'm saying is that, look, at the point that I became vulnerable, there were goods that were assigned to her in the past, the irrevocable decisions you have made. So say there's some good G, the optimal was giving some delta fraction of the good to this agent, but you did not, the algorithm did not. So, but when the algorithm did not, but this, like at this point, eta star over 2 value is left for the agent. So that's why I is vulnerable. So it has to be the case that the agent has lost at least eta star by 2 of its optimal value. So if you like, as an analysis, if you compare the wrong decisions that you have made, by this time you have already, like, goods that should have been assigned to I are fractionally assigned to somewhere else, and that value is gone, right? So this is just because even if I now give you everything, you'll only get eta star by 2. Okay, but this is, note that every time I take delta, which is supposed to be given to I in the optimal, and give it to some other agent, I'm actually doing a greedy thing. That delta fraction that I'm taking from a vulnerable agent I and giving to, say, some agent A, that agent A has higher value for the good than I. So in terms of social welfare, I'm doing better. Let me say this again. Pick a good G, and let's say this delta fraction of the good in the optimal was given to I, but you gave that fraction to some other agent A. Your decision must have been that agent would have been the one that has the maximum value for it. That's the greedy decision. The factor 1/3, I'm ignoring that, so just to squint your eye a bit. But what I'm saying is this delta fraction, instead of going to I, has gone to some other agent. That agent must have had higher value for the good. It's only then that you have done this pass, done this transfer. So what it means is that the social welfare of the algorithm is actually at least as much as the social welfare you have lost among all vulnerable agents. So if for every vulnerable agent, this much social welfare is lost, you have reassigned it, but you have reassigned it greedily. So you've done a better job, at least in term, you have assigned it to higher value agents. So you have this inequality. Social welfare acquired is at least as much as social welfare lost. What this means, and if you eta star cancels out, is that the vulnerable set at no point of time is of cardinality more than 2n. You're always maintaining this invariant that not too many agents fall in this regime of being vulnerable. And that is it. The point is that I am still assigning uniformly among V. So as soon as an agent I becomes vulnerable, from that point onwards, she's only competing with other vulnerable agents for at least 1/3, for this 1/3 of the good that I'm uniformly distributing. So that 1/3 actually, so you have eta star by 2 value total left. This, again, there should be a 2 here, because it's eta star by the cardinality of, moving cardinality of V. But what this ensures is that, right, you have of this, what is left, eta star by 2, you are getting a 1 over cardinality of V fraction, which is again eta star by square root. So yeah, it's a rough sketch, but I hope like the idea is clear. What I am doing in this case is using the social welfare calculation to bound that there will never be a lot of agents in the vulnerable set. And hence, so say vulnerable set was always small. In fact, that's exactly what we are showing. A uniform distribution over it kind of guarantees, even if you land up in the vulnerable set, you will get a sufficiently high value. All this means is that every agent, I'll guarantee, gets at least eta star by square root n, and that's the competitive ratio I told you. The log n terms I'm hiding and so on and so forth. But yeah, I hope the sketch is clear. So here, yeah.
Just a thought experiment. Why did we allocate anything at all to the greedy? Why did we do that? Just to get the bound that every the person who, why did we do that? Why not assign everything to the uniformly first and then to the vulnerable people?
Oh, you mean this step?
Yes.
Oh, it's this step that actually gives me this inequality.
So that's the part I'm trying to understand. So
let me try to like repeat and see if I can. Should have like made more, written more equations, but here's sort of what I'm trying to say. So imagine a good G, any fixed good, and let's say this good was completely assigned to a vulnerable agent. The optimal completely assigned it to I.
Yeah.
Fine. Then, however, what you are doing is just this greedy thing. You're completely assigning to this agent A. But the choice of A ensures that VA of G is more than VI of G. You are looking at, so the I is vulnerable, so she is active, which means that I picked agent A instead of I, means that the value that A had for that fixed good G was more than I's value.
Right. Whomever opt gave to. That's the thing.
Exactly. Whomever this greedy gave to has higher value.
Then, yeah. Okay.
So you are misassigning this good, say, entirely to A, but this misassignment will not hurt you on social welfare front.
Right. Vulnerable agents are subset of active agents. And so
Exactly.
a really highly valuing vulnerable agent would also be considered during the greedy allocation. So if there's
Exactly.
something there, that person would be a candidate to be assigned. So I'm not actually missing out on anything.
Exactly. So, yeah.
Okay.
So this by definition is always a subset of B.
Right. Okay.
Yeah, and if you think this was confusing, please go and read the paper. You'll have fun. But yeah, it does. In all seriousness, these are sort of nice ideas that kind of go in, and it's sort of a surprise still to me that like a single template like kind of works for, gives us this entire slew of results. So that's this reference. As I said, this is joint work with Arindam and Arnab. I'm slightly behind schedule, way behind schedule. So let me just quickly talk about indivisible goods. So this will be the last part. Slightly less technical. I'll try to give you more of a survey of this sort of results in this space. It's, as I said, this is actually one of the more active threads in this picture here. Maybe dozens and dozens of papers quite regularly in this space, and very nice and challenging algorithmic problems. So final leaf, I'm now going to talk about fairly dividing indivisible goods, so a discrete optimization problem. And as always, my objective will be p-mean welfare. So how does the problem look like in this combinatorial setup? Well, now what I have, as before, are n agents, but the decision I have to make, the algorithmic output, is a partition. So I have m goods. These are not divisible anymore. This is not a K. These are discrete indivisible goods. So the problem at hand is the following. I have to find a partition of these goods. So these pairwise disjoint subsets where A1, this subset of goods A1 is assigned to agent 1, subset of goods A2 is assigned to agent 2, and so on. So I have to make this allocation decision and just go over all such allocations to find one that maximizes this p-mean welfare. So what's important to note here is that now VIs are set functions. So for every agent A, the preference, the cardinal preference is specified by the set function VI. So for agent I, VI tells me what is the value that agent I has for different subsets of goods. So, and these set functions can be complex. In all its generality, these are entities that live like that need, let's say 2 to the m amount of size table to even specify. So huge, complicated objects in complete generality, but of course it's too unwild, like it's too wild. We'll kind of look at the standard valuation classes and talk about results in that space. But this is the general form of the problem when I'm dealing with indivisible goods. I'm looking now at a partitioning problem, looking at a problem where the goal is like this combinatorial optimization exercise. Okay, and as I said, of course, the VIs are set functions. They, for every subset of goods, VI tells me the value, the numeric value that the agent I has for the subset. And the algorithmic results obviously are going to be based on different valuation classes. What are VIs? Based on that, the problem becomes easy, hard, tractable, very intractable, so on. So two special cases of this general boxed problem has been studied relatively much more than the general p-mean form. One is social welfare, that is the standard arithmetic mean. It's kind of an important problem in mechanism design, specifically in combinatorial auctions. So you can look at, for example, the textbook on algorithmic game theory by Nissan and others, in that the parts that deal with combinatorial auctions focus a lot on social welfare maximization. It's an important problem that has received a lot of nice algorithmic ideas, rich literature on it, even like before this p-means idea sort of came to the forefront. The other extreme has also been studied, which is referred to as the max-min allocation problem or the max-min fairness, which is egalitarian welfare. You want to find partitions that maximize the minimum value across agents. So the maximize min of VI, AI. Restricted cases, this is also referred to in algorithmic literature as the Santa Claus problem. So again, nice use of things like hypergraph matching, configuration LP. So good amount of literature in this space as well. But let's kind of move, I'll give you references. You can look up those special cases. For general p-mean, the problem is rather challenging, specifically if you go up to like encompassing valuation classes. So this is joint work with Umang, who's here chairing the session, Anand and Ranjini. What we show is that for this broad class of sub-additive valuations, I'll not really spell this out, what sub-additive means, but these are, think of them as the most general class for which you can hope for positive results and complement-free valuations. For them, what we obtain is something like order n approximation. So sub-additive is a broad class. It includes, as very special cases, submodular, additive, XOS valuation. So it's a rich class. For this, we show that you can get an order n approximation for p-mean welfare for all p. Nice combinatorial algorithm. Similar result was obtained by, at least the approximation guarantee was obtained by Chaudhary et al. And if you think this is not a great approximation factor, well, here are my two defenses. First is that we actually show this is tight in a standard Oracle model. So in this setup, I can't really spell out the entire valuation. Like I can't give you, for this subset, this is the value, for this subset, this is the value. That's an exponentially big input. So algorithmic results deal with this by working with valuations that are specified through an oracle. So you have an oracle, you submit a subset, the oracle returns what is VI for that subset. So that's called the value oracle. And what we show is that in such value oracles, this order n is tight. You can't, that's it. Like this is the best you can hope for when you are dealing with sub-additive, or in fact, a class below, which are called XOS functions. So that's the other defense I have for this approximation guarantee, that in many cases, the number of goods can be large, but the number of agents participating in the fair division exercise is not astronomically large. So you are, say, dividing inheritance, and is the number of siblings, which can be manageable, but nonetheless, from a theoretical perspective, and if you are confined to value oracles, this is the best you can do. For now, the sort of point is right. It's hard for general valuation class, hard as in its order n approximable and theta n approximable in the value oracle model. What can you do for special classes? So the joint work with Ranjini, we show that, okay, drastically things improve if you assume that the valuations are identical. So they're still sub-additive. These VIs are a general valuation class, but it's the same for all agents. All agents have the same preference. Makes sense in certain settings. And here, if you use what is called a demand oracle, you can actually get a constant factor approximation. And what's kind of nice about this result, I have not mentioned it explicitly in the slides, that what you get is like a universal guarantee here. So here you can find a single allocation that achieves a constant factor guarantee for all p-mean welfares simultaneously. So I'll give you one allocation and I'll tell you, you know what, go pick your p, and this single allocation that I've given you will be within a constant factor. Its p-mean welfare will be within a constant factor of the optimal p-mean welfare. So the optimal can change. You can change the p, but I'll just give you one fixed allocation. This is the case when all the valuations are identical. There's a very nice recent work by Babayev et al. That look at sort of binary submodular case. So these are matroid rank valuations. So these VIs are rank functions of matroids. In this case, again, you can get a constant factor approximation for all p-mean welfare. So this is for the general p-mean. I mean, the sort of one-line summary here is that, yeah, this is a challenging problem, particular even for p, when p tends to minus infinity. The egalitarian welfare itself is challenging. So it's hard to get sweeping positive results. But what about Nash social welfare, right? Like so again, a very important element in this spectrum of welfare functions, the geometric mean, what can we do for that specifically? And this is a very sort of active and bubbling like thread of research, many papers, many groups working on this. It has a biased list. This B is me most, and but yeah, like lots of, I'll point you to surveys that actually cover the literature a bit well. And you can obtain, again, depending on the valuation class, like a range of results. So for example, if the valuations are additive, so VIs are additive functions, so your value for a set is just the sum of values of the goods in that set. In that case, the best known approximation guarantee is E to the 1 over E. And for technical prowess, you can look at this, like results in this space. So there are prior works that use, for example, real stable polynomials to achieve approximation guarantees for additive, use like novel convex relaxations, like spending restricted ones to obtain constant factor guarantees in this space. So yeah, bunch of work here, and for slides like bit generalizations like budget additive and so on. So good set of results, like nice technical depth here. There's a very nice recent work by Wondrak and Lee, which achieves a constant factor guarantee for the case where these VIs are submodular. So it uses multilinear extensions, so on and so forth. And I mean, if you're looking for like complicated results, so there's a recent work with Pooja Shivaka, I think, who's also attending the talk, Anand, where we kind of use demand oracles and obtain like the break this order n barrier that I mentioned for subadditive, but for a class below, which is called XOS. I'll define this class in the next slide. Yeah, so again, complicated results are there. It's a Saturday, let me just pick one that's sort of easy to describe, and like, I have 5 minutes, Umang.
Yeah, please go ahead. I think
yeah, so I'll wrap up, and with this final result, it's sort of a joint work with Paritosh, where we obtain a constant factor guarantee for this class of valuations, which are called binary XOS. So I'm going to present an approximation algorithm to solve this Nash optimization problem for VIs that are binary XOS. So that's the final step. I'll give you some like literature and point you to certain surveys and then sort of stop there. Okay, so what are XOS functions? These are valuation functions, and in this case, these are set functions that are defined to be pointwise maximizers of additive functions. So in particular, I will focus on what I call binary XOS. So these are a special kind of XOS functions, and you can think of them as a function that's specified by a set family. So I'm not saying that this entire set family is given to you as input, or not even saying that this is a small, like a polynomially small set family. I'm just saying V is a set function. It's defined, say, over a universe of elements. And how is it defined? It's defined by considering this potentially large set family. So each F1, F2 are like subsets themselves. And for any set of elements S, for any set of goods S, the value that you have for this set is obtained as follows. So you go through this entire family, pick each set, look at the intersection, the size of the intersection, and then select the maximum one. So that's the definition of what it means to be binary XOS. If you sort of, instead of looking at the intersection, if you replace this by some additive function, you get the general XOS. I am, for the purposes of this specific result, looking at valuation functions that have this form. They do include interesting special cases. For example, if each of these FIs are independent sets of a matroid, then V becomes the rank function of the matroid. Right? So you're just looking at the largest intersection among all independent sets. That's a matroid rank function. This is more general. I'm saying I'm imposing no structure on these FIs. This is any set family, and you just obtain it this way. Let me repeat the fact that I'm not saying that I am going to give these FIs to you as explicit input. I'm just saying you have Oracle access to V. Just so happens that this V always has this form. There's some implicit large family. The function values are coming out of that. So note that because I'm looking at cardinalities, these things are Like for any S, the function value is the V value, the value of this set. It's going to be at most size of S. But yeah, these things also have like binary marginals, so on and so forth, and hence the word binary XOS. Useful class, in the paper, we spell out some like use cases where and point out the fact that they can be used to say capture preferences in like spatial or temporal settings. So think of these FIs as contiguous slots on a machine. How many of them do you get? That's the function value. So that's a function class I'm going to look at. And in fact, yeah, let me again, like last time, go overboard by a few minutes, but it's a short result. So focusing on binary XOS, this is I'll give you another connection between NV freeness, a sort of a slightly grander form of NV freeness, and Nash social welfare. So sort of hammering in this like relation between these two notions a bit deeper. And for that, let me define two things, right? So I start with any allocation. So this is a partition of the n goods. Now for every agent, I define two sets. Let's say HA and GA. HA is a subset of agents. These are agents who are getting subsets of size 4 more than A herself. Okay, let me say that again. Pick any arbitrary allocation, A1 through AN. Pick any agent A. Look at all other agents that are getting like 4 times as many goods as A. So in the binary XOS case, you can ensure that the value and the cardinality are aligned. So that's why this makes sense. I've replaced values by cardinality, but if you want, you can think of this as being values, and both are interchangeable in this specific context where I'm looking at this specific, like this valuation class. So these are high agents with respect to A. They are getting 4 times as many goods as A herself. Okay. And GA be the grand bundle. It will be the bundle of all such agents, right? So I look at all agents who have really larger number of goods than you, and I club all their goods together. This is my set GA. Okay. So is the definition clear? Okay, so these are the two sets, and here's the lemma. I'm not going to prove it. It's a subtle counting argument. It's a careful counting argument. But what it says is that if you give me an allocation where I do not envy this grand bundle by more than a factor of 1/2, sorry, there's a typo. This should be A. What I'm saying is that for every agent A, the value that she acquires from the subset that's been assigned to her is at least as much as half of this grand bundle GA. Then the number of agents that are alpha suboptimal is at most n by A. So slightly, as I said, it's a careful counting argument. I'll not give you the proof, but this is an NV to Nash kind of a statement. I'll show how Nash comes in. But what interestingly I'm arguing is that, yeah, like you are not envying this entire set. And one can show that standard relaxations of NV freeness does not work. This strengthening does. So I don't have envy not just against these agents individually, but against their entire collection of goods. The second part is important. Let me just explain that, and that will clarify the whole lemma. When I say alpha suboptimal agents, I mean agents who are getting value less than 1/alpha times their optimal thing. So the second part, the implication of the lemma is that I look at all agents for whom the value in the allocation is 1/alpha less than the value in an optimal allocation. The number of such agents S is at most n/alpha. And this holds for all alpha. So I'm saying, okay, how many agents are 4 suboptimal? They are getting 1/4 times the optimal. What the lemma says is, oh, if the allocation has this property, then the number of such 4 suboptimal is n/4. And I ask you, okay, how many agents are 16 suboptimal? Well, you can say, okay, how many agents are getting less than 1/16 times their optimal value? You can tell me that, oh, it drops linearly, it's n/16. How many are getting log n? Then that will be n/log n. So for any alpha, this holds true. So great. And that is it. I am slightly over time, just bear with me. This is sort of the last technical slide. Once I have this lemma, I'm not going to prove it. It holds for binary XOS. But this, does give me a constant factor guarantee for NAS social welfare. Why? Let's just look at the ratio of the NAS social welfare. So the numerator is the one that's achieved by this allocation that has this sort of a grand NV guarantee. The denominator is the optimal NAS social welfare. It's the NAS social welfare of an optimal allocation. So I can just write it as a product of these ratios. The 1 over n exponential, like the exponent stays out. Now what I do is partition them among, like I look at d-adic values of alpha, so powers of 2. For each such thing, the ratio is like 1 over alpha, or within like 1 over alpha and 1 over 2 alpha. So this 2 to the k, think of this as the alpha. The number of such agents will be n over 2 to the k. So when you multiply this 1 over n, you essentially get 1 over 2 to the k. So all I'm doing is applying this result for alphas that are powers of 2. So for alpha equals 2, 4, 8, so on and so forth till infinity. And this is the expression I get. If you work this out, this is a nice exercise and series at this sort of a product of 1 over 2 to the k to the power 1 over 2 to the k is close to 1 over 16. So that gives me the approximation guarantee. Fine, like even if the technical details weren't clear, what I'm saying is that this is a nice property to have. Like if you have such an implication, this proof actually does not require anything about binary XOS. What I need the binary XOS is to show that such grand NV freeness implies this sort of linearly decaying suboptimality, but yeah, it's a good takeaway to remember. Like if you can establish such an implication for other valuation classes, you will again get a constant factor approximation guarantee. So you just ensure that like the number of alpha suboptimal like drops as a factor of alpha, a good property to have. Okay, that's the theorem, which means that if I have such grand NV freeness, I do have constant factor approximation guarantee for NAS social welfare. There's a simple potential way of achieving such an allocation. You should keep doing local updates. You can find such an allocation. I'll again, in the interest of time, spare you the details. These are the two papers I talked about, the online result and this binary XOS case. Yeah, many interesting problems. I'll in fact point you to the survey next slides that have many more nice questions in this space. But yeah, the one that I like is this one that I told you that for identical valuations, you can get a constant factor approximation guarantee for even subadditive ones, subadditive valuations in the demand oracle case. Can you extend that, right? So can you look at fair division instances where there's a fixed number of distinct valuations? So the number of agents can be large, they can be n, but I'm saying that let's say there are only 4 different valuations. So each agent has one among these 4 different valuations. For those sort of instances, can you obtain a nice approximation guarantee? So that's I'm referring to that as bounded heterogeneity. So that to me would be an interesting results. Yeah, query communication results, NAS social welfare for in this more general Oracle models. Here are the surveys that I've been promising you for quite some time. Like as I said, less than a month old actually. Both are on archive with great open questions dealing with different forms of NV freeness, and so going beyond just p-mean welfare and so on. There's a nice survey by Varut also that talks about constraints. I've looked at the unconstrained problem pretty much. Yeah, so this is also a good read to understand the landscape of results. These are the textbooks I mentioned last time, way over time. So just quickly stop here and thank you for your attention. Yeah.
Great, thanks a lot, Siddharth. Maybe a quick question.
Yes, yeah.
So I'll just ask one. So you mentioned the Banerjee et al. Result, right? So there also, do they assume that the sum of this normalization? I guess they do, right? You said because without that you can't get any guarantees.
Yeah, they do. They assume something. They work with something which is called algorithms with prediction. So they assume that I have a estimate of this total.
Oh, I see.
And okay, as your estimate degrades, your quality degrades. But if it's exact, then that robustness is something that is nice to achieve for say like egalitarian and so on. So that's a good, yeah. This is an active like subfield, right? Online learning with, or online algorithms with online decision making with predictions. So that's the flavor of their results. Yeah.
Okay, so I guess let's have maybe a 2-minute break before the next talk. And thanks a lot for that fantastic talks, both of them.
Thank you.
Right.
Hey, sorry, I keep eating up the break time. I think you're muted.
Whether you're muted.
Sorry, there is a 15-minute gap, so no harm done.
Okay.
Hi, Kavita.
Hi, can I share screen?
Yes, you are co-host.
Okay.
Hi, good afternoon, Sushmita. Hi, Kavita.
Hi, Meghna.
I'm glad there are so many participants left. I thought everybody would log out by Saturday afternoon.
We are looking forward to learning more about popular witness.
Oh, thanks, Meghna. That's very sweet of you. So how are things at IITM? Do you have in-person classes?
We are going to begin soon. We are allowed to do so from 10th of March, but still students are coming in and so on. So each instructor may do it according to the class size and other things.
I see.
What about at TIFR?
Yeah, so from February 1st or so, February 15th or so, we've been allowed to have in-person classes. But as you said, some people are still continuing with online.
Yeah, because some students are not yet in. So half the class is here, half the class is not here. And so.
Right. So we have also been told the class should be only half full.
Oh,
So,
I think we are doing away with most restrictions. Sushmita, are some of you at IMSC attending it together?
Not really. I mean, I'm in my office. The students must be in their, offices or wherever. So, I mean, I imagine on they're near the desktop or something, because few days ago, Wi-Fi wasn't working very well, but it's not like we don't have like a viewing session, like, like an auditorium or anything like that. I guess with the COVID thing, 2 years of home isolation and so on, doing that sort of thing would be actually a little strange now. But I know that students are organizing movie viewing evenings and so on and so forth. So I guess they're inching back to that sort of thing. But I think teachers are still, us probably still trying to get on with online classes. Let's see. So, in our institute, obviously the students are not, it's not like an IIT, right? Where you have huge classes and lots of students are taking certain courses at least. We have small room, a few students, but the rooms are small, and because of the central AC, there's not a lot of good ventilation. That's another thing. If you could just have classes out in the open, like in a park or something, it could very well work for us. At least the type of size of classes we have at IMSC. But and we have these. Have you? Maybe you must have been to IMSC, no?
Yes, sure, yeah.
So, Kavita, have you been?
Oh yes, many times.
Okay, so there are those huts, no? The small huts, have you seen, where people used to go and sit and have? I have seen some faculty members actually hosting classes there. I see them, like there's a faculty member and there are some students sitting by. So I guess that those are classes or maybe just discussion. So that's very tempting to do it. Then physical classes would not be so much of a problem. So, there was somebody saying there was an issue with I don't see this person. Gayatri, are you around?
Yes.
Gayatri. Okay, so I don't see him. The person who sent Vishwa Prakash. So I guess it's...
Even I don't see that person.
Okay, never mind. So we just wait 2 more minutes and then we can start, maybe?
Yeah.
So this is the last session for the day as well as the workshop. Time flies by.
So what's your answer now when I asked you how's the workshop looking? You said ask me on the last day.
1 more session later. Still many things could go wrong. But yes, but it has been above and beyond anything I could have anticipated or expected. It really is, it has been delightful. And it's I'm really happy, and the students seem to have liked it. They enjoy it. They said they were able to follow a large portion of all the first part 1 talks and so on. So, what more can we expect? And then there'll be YouTube videos. People who want to follow up, they can do and write to you people and so on. So that way it seemed, at least, after the hiatus of a year, we are at least getting back on schedule. So hopefully next year would be even more smoother. This one there's a bit of hesitation as to how it will work out and so on. So that way I'm very, very pleasantly surprised. Not surprised, very happy with the way things have, but still 1 session to go. Let me. So,
shall we get started?
Sure, please.
Yeah. Okay, good afternoon, everybody. And I welcome you again to the second talk of today afternoon. And this is the second part of the talk by Kavita, who is a professor at the School of Technology and Computer Science at TIFR. Yesterday she told us about popular matchings and witnesses in 2-sided preferences, as well as the popular assignment problem in the 1-sided model. We'll learn more about it from her today in her second talk. So welcome to you.
Thanks, Meghna. And as this is the last talk of this workshop, on behalf of all the participants, let me take this opportunity to thank the organizers. Thank you. So I think it was a really nice workshop, and thanks so much for the effort you put in.
Our pleasure. I don't know, where is Vikram and Oitra? Can you please unmute yourself?
Yes.
Thank you. Thank you.
Thank you.
So let me begin. So this is a continuation of what we saw in the second half of my talk yesterday. We are dealing with 1-sided preferences. So we have a bipartite graph One side is the set of agents. Only they have preferences. Only they cast votes. The other side are inanimate objects, as in this example. And the problem we were looking at is, does G admit a popular assignment? That is, we're interested only in perfect matchings here. And among perfect matchings, is there one that is not defeated by another perfect matching? So that's the popular assignment problem. And we also showed a polynomial time algorithm to solve it. So for the first maybe 15 minutes today, I would like to go deeper into proving the correctness of this algorithm. So let's just recall. So we use this edge weight function. Given a perfect matching or assignment M, there is a corresponding edge weight function as shown here. Weight of an edge is just, does the agent endpoint of the edge, that is, does A prefer the other endpoint to her assignment in M? If so, it's +1. If she in fact prefers her own assignment, it's -1. If she's indifferent, it's 0. And an assignment is popular if and only if a max weight perfect matching under this edge weight function has weight exactly 0. So this is the LP for max weight assignment. So by now, I hope you're familiar with this LP. And M is popular if and only if the optimum value of this LP is 0. So let's take the dual LP. It's a really simple looking LP. The variables are the alpha values. And we had this claim that M is popular if and only if there exists a dual feasible solution alpha such that the sum of all the alpha values is 0 and the alpha values of agents are in this set 0, 1, 2 till n-1 and the alpha values of objects are minus values of this 0, -1, -2 till -n-1. And then we introduced this subgraph G sub L. We said G has a popular assignment if and only if there is a level function L from the set of objects to this set 0, 1 till n-1 such that this subgraph G sub L has a perfect matching. So if it has a perfect matching, we claimed that was a popular assignment. And the proof of that was, in fact, we can construct a witness as shown here. So the alpha value of any object is the negation of its level, and the alpha value of any agent is the level of its partner. And if it has a popular assignment, it has a dual feasible solution alpha, and that would in fact define the levels of objects. So it's both ways. So let's just recall what is this G sub L. So given any such function L, we can define the corresponding subgraph G sub L. For any agent, let's define L star A to be the highest level at which it has a neighbor. And the edge set of this subgraph is exactly those edges AB between an agent and her most preferred neighbor at the highest level. And she's also allowed to look one level down, one level below the highest level. She can also put edges to her most preferred objects in this highest level -1, provided these objects are strictly preferred to her favorite objects in the top level. So let me just pause for a minute so that you can read what I've written here. EL has exactly those edges AB, where level of B is the highest level for A, L star A, and B is the most preferred object for A in this level, or LB is one level below, and B is the most preferred object for A in this level, and A prefers B to all her neighbors in the top level. So the pseudocode of the algorithm was quite simple. Let's start with all objects on level 0. And while there is no object at level n, so while all levels are less than or equal to n-1, let's do the following. Construct the subgraph G sub L and find a maximum matching. If it's perfect, great, return M, that's a popular assignment. Well, if it's not a perfect matching, then we go to the step below where we say, let's increase the levels of all unmatched objects. And in case the level of any object becomes equal to n, we say, return, there's no popular assignment. So in case we return a matching, the fact that it's a popular assignment is the easy side actually. So we can prove it's a popular assignment by constructing a witness for it, and the levels basically give us this witness. Alpha of B will be equal to minus of its level, and alpha of any A will be equal to level of its partner. And it's easy to show that this is indeed a dual feasible solution, and by construction, the sum of all the alpha values is 0. So let me go to the more difficult side. When the algorithm says G has no popular assignment, that indeed G has no popular assignment. So when does the algorithm say G has no popular assignment? It means the level of some object has reached N. So let's say L was a level function when the algorithm terminates. So L of B equals N for some object B. Now suppose G indeed had a popular assignment M prime. Let alpha prime be a witness of M prime. So the claim is, so let's look at the corresponding level function L prime, which is just minus of alpha prime B. We claim that for any popular assignment M prime and any witness alpha prime of M prime, our L function, our L value, the level of object B as per the level function L constructed by the algorithm is a lower bound of that L prime B. So the claim is L prime B is at least L of B. And so if L of B equals N, it means L prime B is also at least N. But that's a contradiction because by definition, alpha prime B has to be in this set. That's a definition of a witness, has to be in the set 0, -1 till -n-1. So L prime B by definition has to be at most n-1. So if L prime B is at least N, that's a contradiction. So this some of this sort of minimality that this claim is showing is a very powerful property. So we are claiming that for any popular assignment and any witness, our L value is a lower bound for the level of any object under any assignment. So assuming the claim, if it is indeed the case that L value of any object equals N, then G has no popular assignment. Is this okay? So this is taking the claim as a black box. We'll prove the claim in the next slide.
Yes, sounds okay. Yeah.
So let's say at the start of any while loop, it is indeed the case that our current L value at the start of the while loop iteration, let's call it L subscript old. If L old B is less than or equal to L prime B for all B, then we will prove that by the end of this while loop, this remains an invariant, that this inequality is still maintained. And this inequality is certainly true right at the beginning because all L values are initialized to 0. So the technical lemma is that if an object B is unmatched in a maximum matching in G sub L, then in fact, this inequality is strict. It is the case that L prime B is strictly larger than L old B. So if you recall, we increase the level of an object only if it's unmatched in a maximum matching in GL. So for any unmatched vertex, any unmatched object B, because of the strict inequality, it has to be the case that L prime B is at least L old B plus 1 and L new B is exactly L old B plus 1. So the L value of an object changes only if it's unmatched in the particular maximum matching that we computed. So you should not say in a maximum matching, we should say in our maximum matching. And for any matched vertex, we left the L value alone. So at the end of the while loop, our inequality will still be maintained. So the lemma basically is claiming that the inequality is strict if, sorry, I should have kept saying our maximum matching. So please replace a maximum matching with our maximum matching, with the maximum matching computed by our algorithm. Yeah, so let's prove the lemma.
Kavita, can I ask one question in the previous slide?
Please.
Yeah. So this first I itemize things. So for any unmatched vertex B, now it's true by the way the algorithm was defined, L new of B, the new label of B should be L old of B plus 1 because B is unmatched, right? In the current matching. But why should that be at most L prime B? L prime B is that solution that exists and the labeling with respect to that witness, right?
Exactly. So this is what the lemma is saying. The lemma is giving us this guarantee that it is strictly larger and they're all integral values. So it has to be at least L old B plus 1.
Isn't this that implication sign in the statement of lemma? Doesn't it mean that implies B is unmatched in a maximum matching in GL?
No, it's in our maximum matching. So
Okay. Implies L prime B is strictly greater than L old B, right?
exactly. So,
So-
if B is unmatched in our maximum matching, then it has to be the case that L prime of B is strictly larger than L old B, which means it is at least L old B plus 1.
Are we not proving this lemma? We are taking this as a black box.
For now, we're taking it as a black box. In the next slide, I'm going to prove it.
Okay, so I was thinking that is the, okay, all right, thank you.
No. So this is a technical lemma. So
Yeah. Okay.
the proof will take 2-3 slides.
Okay, so using this lemma, that thing follows directly.
Absolutely. So using the lemma as a black box, we are done. So the whole task is to prove this lemma.
Sure.
Exactly, a proof of the lemma. So again, let M be our maximum matching in G sub L old, and let B0 be an unmatched vertex, unmatched object in this matching. We need to show that L prime of B0 is strictly larger than L old of B0. So our matching is a maximum matching in this graph G sub L old. So the symmetric difference between M and M prime, it has an augmenting path because M prime is an assignment. It's a perfect matching. And M was not a perfect matching because it left at least one object unmatched. So let's look at this M augmenting path P, which has B0 as an endpoint. So there has to be some edge in this augmenting path that's not a part of our matching M. So let's call that edge AT-BT, and let's examine the prefix of this augmenting path, B0, A0, A1, B, A1, B1, so on and so forth. And the last edge, let's terminate this augmenting path till this edge, BT, AT. So as shown in the figure, so just start from the top, B0, A0, dot, 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 and let's focus till the last edge, BT, AT. That is not, this edge is not present in our subgraph G sub L old. So M prime is a perfect matching in the corresponding subgraph G sub L prime. So if you look at this figure, the dashed edges are in M prime, the solid edges are in our matching M. So let's first show that L prime of BT, which is in fact the bottommost object in this path, the L prime value of that object is strictly larger than L old of BT. So let's first show that. Our whole job is to show that L prime of B0 is strictly larger than L old of B0. But let's start at the bottom and then we'll move to the top. So since this edge AT-BT is not in the edge set of the graph G sub L old, so one of these three cases has to hold. Either AT has a neighbor in level at least L old BT plus 2, or it has a neighbor one level higher, that is L old BT plus 1, that's at least as good as BT, or it has a neighbor in the same level that's better than BT. That's why this edge is not present in our graph G sub L old. So that's the definition of the graph G sub L old. So if an edge is not present, it's because there is a neighbor at least 2 levels or even higher, or there is a neighbor 1 level higher that's at least as good as this object, or there is a neighbor in the same level that is even better. So suppose L prime BT equals L old BT. Since at the start of the while loop iteration, we had L prime B is at least L old B for all B. For each of these three cases, the conclusion is that the edge AT-BT should not be in E sub L prime either. And that's a contradiction because M prime is a perfect matching in G sub L prime. And so this edge is very much present in G sub L prime. So if it's the case that L prime of BT equals L old BT, then in fact this edge ought not to be present in the other subgraph either. But M prime is present in the other subgraph. M prime contains this edge, so this edge better be present, and the only way it can be present is that L prime BT is strictly larger than L old BT. So for the bottommost object in this augmenting path, well, for the entire augmenting path, but we're just truncating it till this portion. For the bottommost object, as far as this picture is concerned, L prime BT, its level under the L prime function is higher than its level under the alone function. And we show it actually the same inequality has to hold at every level. So let's move higher. Suppose there is an index I such that L prime bi plus 1 is strictly larger than L bi plus 1. However, L prime bi equals L bi. Then in fact, we again have three possibilities. And in each of these three possibilities, we get the same conclusion that the edge, the dashed edge AI bi ought not to be present in G L prime either. So let's go through these three cases. So the edge AI bi plus 1 is a solid edge that's present in our matching M. So AI has two neighbors, bi and bi plus 1. And this solid edge for sure is present in our subgraph. So it has to be the case that either its level is at least one or more higher than L bi, in the level of bi, or it's on the same level as bi, and AI does not prefer bi to bi plus 1, or it's one level lower, and in fact AI prefers bi plus 1 to bi. So if we assume that the level of bi under that L prime function and under our function is equal, but bi plus 1 had a higher level under the L prime function than our function, then in fact we get a contradiction. Because in the first case, the level of bi plus 1 under the other function is at least 2 more than the level of bi, both under that function. In the second case, bi plus 1 is one level higher or more, and AI does not prefer bi to bi plus 1. And in the last case, it's in the same level, and in fact, AI prefers bi plus 1 to pi. So in all the cases, the conclusion is that AI bi ought not to be present in that subgraph, G sub L prime. However, we know that the dashed edge is present in the other subgraph. So it has to be the case that if bi plus 1 has a higher level under the other level function, then even bi should have a higher level. So this moves upwards. All the objects on this truncated augmenting path that we saw have higher levels under the other level function compared to our level function. So finally, the topmost object B0 also has a higher value under L prime than our level function. So all this follows from the construction of our subgraph, really. So the construction of our subgraph gives us this thing. So going back to our algorithm, when we return G has no popular assignment, yeah, we're not making any mistake. G indeed has no popular assignment. And the running time of the algorithm, that's easy to see. So in every iteration, the level of some object is increasing, and we know no level can even become equal to n. So summation, sum of all the levels is strictly smaller than n square. And so the running time of our algorithm, we keep computing maximum matching in every iteration. There are at most n square many iterations. So the running time is m into n to the 5/2. And as I said yesterday, this is perhaps a nice open question. Can we design a faster algorithm for the popular assignment problem? So now let's look at a slightly tougher problem. Suppose there is a cost function. So the graph has a popular assignment. Our algorithm is able to compute one, but there's also a cost function and there's a budget. And we would like to compute a popular assignment whose cost is at most the budget. So this is basically the min cost popular assignment problem. Can we do this in polynomial time? Unfortunately not. So this is an NP-hard problem, even when edge costs are in the set 0, 1 and agents have strict rankings. So while the popular assignment problem has a polynomial time algorithm, the min cost popular assignment problem is NP-hard. But let's look at a simpler variant of this problem. So this is a popular assignment problem with forced or forbidden edges. So we are given a subset of forced edges and a subset of forbidden edges. And we want to know if there's a popular assignment that contains all the forced edges and completely stays away from the forbidden edges. So a simple variant of our algorithm can solve this problem. So though the min cost popular assignment problem is hard, this particular variant, which is in fact a very well-studied variant in the stable matching literature, this is easy to solve. Easy in the sense there is a polynomial time algorithm. So let's look at this table. In fact, my theme in today's talk is basically filling the entries in this table. The complexity of finding a min cost popular solution. So let's focus on one-sided preferences. So the top right cell is basically saying what I said in the previous slide, the complexity of finding a min cost popular max matching. That's a min cost popular assignment. That's an NP-hard problem. However, the complexity of finding a popular assignment with forced forbidden edges, everything with one-sided preferences, we know the complexity. And the clean combinatorial characterization of popular matchings in one-sided preferences tells us that, in fact, the top left entries, both the cells are polynomial time. So P is polynomial time. So let's focus on let's go back to two-sided preferences and ask the question, what is the cost of finding a min cost popular max matching with two-sided preferences? So we've not even defined this problem. So here we're given a bipartite graph, and back to the starting model, every vertex has a strict ranking of its neighbors. So this is the stable matching model. However, we're interested only in maximum matchings. So in fact, there are many applications for this problem. Allocation problems in humanitarian organizations. So cardinality is the most important attribute, more than stability, popularity, anything. Matching medical students to residencies, you can't just tell someone, I won't give you a residency because my stable matching left you unmatched, right? Everyone has to get matched. So in our example, in fact, the red matching, that's the only maximum matching here. That's the only feasible solution. So in fact, this problem was considered a few years ago by Biro et al. And they asked, what is the complexity of finding a maximum matching with the minimum number of blocking edges? So in fact, this problem arose in Scotland when they had to match medical students to residencies, and a stable matching was leaving some of them unmatched. And so they were asked to find a maximum matching with a minimum number of blocking edges. So they could do it for that particular instance, but they wanted to find the complexity of this, and they showed its NP-hard. So this is a very natural relaxation of stability, and unfortunately, it's hard. So how about a popular maximum matching? So this is a matching that's popular, restricted to the set of maximum matchings. So if you look at the red matching, it loses to the blue matching. So it's not popular absolutely. So smaller matchings may defeat it, but it is undefeated by maximum matchings. So does such a matching always exist? So in one-sided preferences, for sure it doesn't exist. And the whole algorithm was to decide if one exists or not. But in two-sided, and we're in two-sided strict preferences. So in two-sided strict preferences, does such a maximum matching always exist? Can we find one easily? So actually, I looked at these questions about 10 years ago in the same paper as the max size popular matching algorithm. So the same paper has both that algorithm and this algorithm, where in fact, I showed that such a popular maximum matching can be computed in order mn time. So such a matching is always there because the algorithm finds it. So let's just go through this algorithm. It's just a simple algorithm. Every vertex has a level associated with it. Every agent, so let me stick to the same notation. Let's call maybe agents and objects is not fair here. It's not fair here because vertices in V also have preferences and votes. Okay, so let's just go around calling them vertices in A and vertices in B. So every vertex in A has a level L of A associated with it, and every vertex in B prefers higher level neighbors to lower level neighbors. So in fact, that algorithm that we saw for popular assignments, we can say is a kind of borrow some ideas from this one. So we initialize the level of all objects to 0, and at the end, the level of not all objects, sorry, all vertices in A that initialize to 0, and at the end, L of A is in this set 0, 1, 2 till n-1. Sorry, I'm saying objects somehow by just some habit from the previous algorithm. There are no objects here. Both sides have preferences. So the popular maximum matching algorithm is as follows. Let's run the Gale-Shapley algorithm in the given instance. If this is perfect, wonderful. So while there is an unmatched vertex in A, whose level is strictly smaller than n-1, increase its level and it starts proposing to its neighbors all over again. And the Gale-Shapley algorithm continues. So an agent who has been rejected by all its neighbors in level 0 gets promoted to level 1 and starts proposing again. And because vertices in B prefer higher level neighbors to lower level neighbors, a neighbor who rejected this agent in the first round may now find it more interesting and accept it. And the algorithm continues. So return the final matching. So it's not clear that the final matching is a maximum matching, let alone a popular maximum matching. But yeah, so you could look up this paper. It's not a hard proof of correctness, but I won't be doing it here. My focus now is on this question, is on the min cost variant of this. Suppose it is a cost function and a budget. I know how to find some popular maximum matching, but I want to find a min cost one, something that's within my budget. Can we do this efficiently? For popular assignments, the answer was it's NP hard. However, here, the problem can be solved in polynomial time. So the popular maximum matching algorithm, though we wrote it as it's just running Gale-Shapley algorithm across n levels, we could imagine it as running one invocation of Gale-Shapley algorithm on a graph which can be considered as n copies of G taken together. What do I mean by this? So let G star be the graph where every edge is replicated n times. So if you recall the bidirected graph that we saw last time, where every edge was replaced by 2 edges. Now let's replace every edge with n copies. So rather than 2 copies gave us the max size popular matching algorithm. And if we replace every edge with n copies of itself between the same 2 endpoints, so in fact, Gale-Shapley algorithm on this graph gives us a popular maximum matching. So is this G star graph sort of clear? So there are n copies. There we put directions on edges. So here let's attach a level to each version of the edge. So there are n copies of this edge. One copy I'm calling level 0 copy, another copy I'm calling level 1 copy, and so on and so forth, level n-1 copies. So each of these copies of the same edge E has a different level associated with it. And vertices in A prefer lower level edges and vertices in B prefer higher level edges. So between the same 2 endpoints A and B, there are n copies of the same edge. A says, I like the level 0 edge better, and B says, I like the level n-1 edge best. So any vertex in A likes all level 0 edges better than all level 1 edges, and within level 0 edges, it's her original preference order. Within level 1 edges, it's her original preference order, so on and so forth. And vertices on B, on the other hand, say any level n-1 edge is preferred to any level n-2 edge, which is better than any n-3 level edge, and so on and so forth. And finally come level 0 edges. So the proof of correctness of the previous algorithm shows that any stable matching in this graph G star maps to a popular maximum matching in G. So what we showed in this paper last year was this mapping is surjective. That is, every popular maximum matching has to arise in this manner. So yesterday someone asked me this question, if every max size popular matching arises as a stable matching in that bipartite graph, and the answer was no. However, for popular maximum matchings, interestingly, every popular maximum matching arises exactly as a stable matching in this graph, where every edge is replicated n times. So that's what the surjectivity means, that every popular maximum matching, in fact, can be viewed as a stable matching in this graph G star. Which means to find a min cost popular maximum matching, all I have to do is find a min cost stable matching in G star. And there are many algorithms for this problem. Efficient combinatorial algorithms, linear programming based algorithms. This is a very well studied problem. So by using this algorithm, I can solve the min cost popular maximum matching problem. Is it okay so far? Yeah, so we're given a popular maximum matching M. Our goal now is to come up with a level function. So I said the level function is on the edges, but it would be simpler to think of it as on the vertices. So we want to come up with a level function on the vertices so that I'm just saying something here, M and L satisfy stability in G star. What exactly this line means, I'll explain in the next slide. But for now, let's just recall this edge weight function. We are in the world of two-sided preferences. So given a matching M, there is a corresponding edge weight function, which gives every edge a weight of either +2, -2, or 0. Blocking edges get a weight of +2. And if both the endpoints hate each other compared to their respective partners in M, it gets a weight of -2, otherwise 0. So what does it mean to satisfy stability in G star? So I've just drawn the matching as, so AI and BI in the figure just represent vertices whose level is I. So what does it mean for M and L to satisfy stability in this graph G star? So for any matching edge AB, the levels assigned to the endpoints of any matching edge have to be the same. So that would be in a way the level of the edge I was referring to earlier. So if AB is in the matching M, then L of A has to be equal to L of B. And unmatched vertices in A have to be in the topmost level, and unmatched vertices of B have to be in the bottommost level. And for any edge AB, it should be the case that level of B is at least level of A minus 1. So for an edge to move to a higher level, she tried with all her neighbors and they didn't find her current level interesting. That's why she had to get promoted to the highest level, to the next higher level. That's what this constraint is capturing. L of B should be at least L of A minus 1. And for two vertices in the same level, in fact, the edge between them cannot be a blocking edge. The edge weight has to be either 0 or -2. And for an edge AB, where B is one level below A, their edge has to be a kind of hating edge. Both of them should hate each other. So their weight is -2. So this is what it means for a matching M and a level function L to satisfy stability in G star. So we want to claim that given any popular maximum matching, so we're given a matching M, and we're also told it's a popular maximum matching, I can actually construct such a level function so that all these properties are satisfied by that function L. That's our claim. So let's go back to the LP method. And for simplicity, to begin with, let's assume that G has a perfect matching. And let's write the LP for max weight perfect matching. It's a very simple LP. So every vertex has to be matched. So summation XC E belongs to delta U is equal to 1. And if M is a popular perfect matching, then the optimum value is 0. The dual is quite simple. We are not familiar with this. So if M is a popular perfect matching, then there is a dual feasible solution alpha such that sum of all the alpha values is 0. We show, in fact, there's an optimal solution with more structure. So alpha of A is in the set 0, -2, -40, -2 times n minus 1. And alpha of B is in the set 0, 2, 40 twice n minus 1. So let's set the level of a vertex in A to be I if its alpha value is -2i. So just drop the -2 and take the I. And for a vertex in the set B, set its level to be j if its alpha value is 2j. And actually this works. So the levels that you were looking to construct are actually just being produced by the dual LP. So we wrote the dual LP totally in a mechanical manner virtually, but there is so much meaning in these values. So there is a very nice structured dual optimal solution, and we can actually read off the levels from that by just halving these values. And the tougher case is when G has no perfect matching, in which case we need to set L values so that all unmatched vertices in A are in the topmost level and unmatched vertices in B are in the bottommost level. So we again play with the dual LP. So we just drop all the unmatched vertices for now. Then it becomes a perfect matching in the resulting in the remaining graph. So we can just inherit the previous lemma. And now we also claim that for all neighbors of unmatched vertices, in fact, we can pin down the alpha values. Rather than say they just belong to this set, we can say that for all A that are neighbors of unmatched vertices in B, alpha value has to be 0 And for all B that are neighbors of unmatched vertices in A, alpha value has to be twice n minus 1. So the alpha values of neighbors of unmatched vertices have to be the highest possible alpha values in both these sets. The highest possible alpha values for vertices in A is actually 0, and the highest possible alpha values for vertices in B is twice n minus 1. And these vertices that are neighbors of unmatched vertices claim the highest possible alpha values. So this is in fact a technical lemma. And now we set alpha, the L values exactly as before. Just take half the alpha value, take absolute value, and yeah, this works. So the toughness here was to prove the lemma, the existence of such a dual certificate.
May I ask a question? Okay, just looking at this pink magenta text. So it's fair to say that, is it fair to say that a vertex has high alpha values, that level information, because it couldn't find a partner in the lower levels?
So vertices in A always want to be in lower level, exactly. So for them, there is no need to go upwards at all, because they in fact even have unmatched neighbors. So a vertex has to actually move, a vertex in A will move upwards only if she can't find a neighbor, only if she can't find a partner.
What about the B vertices?
So B vertices like to be in as high a level as possible. So they would ideally like to, in fact, propel themselves to the highest possible level. And in fact, they have unmatched vertices who have to keep going higher and higher and higher to find partners. So thanks to such neighbors, they get to move upwards. So there's those neighbors who are desperate and have to move to the highest level, and even there they have not been able to find partners, will naturally keep asking these people again and again and again, will you be my partner? Will you be my partner? And so these people have a lot of, let's say, value in the market because they have neighbors who are ready to do everything to please them. And these people say, well, I want to be in the highest level. These people say, yes, I'm ready to go to the highest level. But even then, they couldn't find partners, these unmatched vertices. Nonetheless, the neighbors have partners at least as good as them, in fact, better than them, because we're in the strict preferences. So it's very intuitive, right? Yeah,
right.
Prove it is
like this, they have to climb up if they couldn't find lower neighbors, and they have to come down if they can't find neighbors, right? And at some point, if they meet each other, that's when the matching happens.
Exactly. But here there are unmatched vertices, so these poor people could not find partners. So.
Right. So this B being a neighbor of an unmatched vertex in A, so all these unmatched neighbors are at the highest level, and this B alpha B who's realizing this 2 into n minus 1 thing, it has already found a partner, right? Otherwise, why should this person be unmatched? Why
exactly.
It have right unmatched neighbor? So it must have found a neighbor at one of the higher levels, so that it
at the highest level.
At
so
the
higher the
level.
better. Exactly.
Right? That's why they have a unmatched neighbor at the highest level. Otherwise, yeah. Okay.
Exactly.
Yeah. All right. Okay. Exactly. Thank you.
Yeah, all this is very intuitive indeed. I'm glad you're able to visualize it indeed, because when you look at the algebra, it just looks like some symbols, some values, but there is a story also.
Yes, that's yeah. But I think you explained it nicely to sort of understand.
So Meghna, how much time do I have left?
Yeah, so we have 20 minutes.
Okay, thank you.
Yeah.
So I wanted to fill up more entries in this table. So in the bottom right cell, I wrote 2 P's because we proved that the min cost popular maximum matching problem can be solved in polynomial time, and forced forbidden edges is a special case of it. So that's also in polynomial time. So we still have to fill out these cells. So let's look at two-sided popular matchings. So there is no condition on cardinality. It's not that cardinality is more important than popularity. We are in the starting model. It's only popular matchings we are interested in. Let's try to see the complexity of finding a popular matching with forced or forbidden edges. So in fact, this was our working example there. And we constructed this bidirected graph yesterday, if you recall. And in fact, we ran the Gale-Shapley algorithm here, and we said any stable matching in this bidirected graph is a max size popular matching in the starting graph. So let's call such a popular matching dominant. What is the characterization of dominant matchings? These are popular matchings that defeat all larger matchings. So not only is the matching popular, Popular just means you're not defeated, but these matchings actually defeat all larger matchings. So that's the class of dominant matchings. So in fact, this is a dominant matching, the green one in the top figure. Suppose we are given a single edge E and we want to know if there is a popular matching that contains this single edge E. So this is joint work with Agnes J. So basically, this is a very well-studied problem in stable matching literature. There are linear time algorithms, simple variant of the Gale-Shapley algorithm that checks if there is a stable matching with a given edge. If there is such a stable matching, great, return the stable matching because that's popular. Otherwise, let's try to find a dominant matching with a given edge. How do we solve this problem? Any dominant matching is a stable matching in G prime. So run the same stable matching with a particular edge algorithm in G prime. If we find such a stable matching, great. That's a dominant matching. It's a popular matching. So we've solved the problem. If we can find neither a stable matching with E nor a dominant matching with E, we claim there is no popular matching with E. And in fact, we show a decomposition theorem for popular matching, and that leads to the correctness of the algorithm. So I won't prove the correctness, but I think it's a nice algorithm. Just 3 steps. Check if there is a stable matching, check if there's a dominant matching. Otherwise, there's no popular matching. So this was a nice story as far as a single edge was concerned. But what about if we are given 2 edges? Is there a popular matching that contains both these edges? Note that there need not be a stable matching with both the edges or a dominant matching with both the edges. There could be a popular matching, but our decomposition theorem says it splits into a stable part and a dominant part. Maybe the stable part has E1 and the dominant part has E2. So it's not that the stable part has both E1 or E2, both E1 and E2, or the dominant part has both E1 and E2. In fact, this is an NP-hard problem. So the minute we go to 2 edges, is there a popular matching with both these edges? We don't know how to solve it in polynomial time. In fact, it's highly unlikely. It can be solved in polynomial time. So in fact, the set of popular matchings, the complexity is sort of quite strange, I feel. So I just marked at the top, we have the set of max size popular matchings. At the bottom, we have the set of min size popular matchings. We know how to find a matching in these classes. The Gale-Shapley algorithm in G prime and in G finds these matchings. However, is there a popular matching that's neither max size nor min size? So in that entire part in the middle, is there even a single matching or is it empty? Just to answer this is an NP-hard problem. So the complexity is like this. Finding a max size popular matching is easy. Finding a min size popular matching is easy. But trying to find something that's neither max size nor min size is NP-hard. So now we can fill up the last entry also. So in fact, with even 2 forced edges, it's NP-hard. For sure, the min cost popular matching problem is even harder in the sense. If even the special case is NP-hard, the general version is of course NP-hard. So we have filled out all the entries, and strangely, the 2-sided preferences popular matching problem has turned out to be the hardest of the lot. So both the cells for that are NP-hard. So this motivates, why not relax matchings to fractional matchings? Yesterday in Amit's talk, we saw he was doing fractional set cover. Today, Siddharth was doing again fractional allocations. So similarly, we'll do fractional matchings. So let's say we have students and advisors, and we want to match them optimally. Of course, we don't know how to find a, let's say, max utility or min cost popular matching. But maybe student can have 2 advisors. So he's half advisor is A, half advisor is B. Maybe we can come up with a fractional allocation, fractional matching that somehow optimizes how well things can pair up with each other. So what is a fractional matching? So the convex hull of the edge incidence vectors of all matchings, that's a matching polytope, is described by these constraints. And any point in the matching polytope is a fractional matching. So it's a vector in Rm that satisfies all these constraints. And it can be expressed as a convex combination of, so I subscript mi is just the edge incidence vector, the 0, 1 vector corresponding to a matching mi. So X can be expressed as a convex combination of some matchings. And the notion of popularity extends to fractional matchings also. So to compare a fractional matching with an integral matching n, let's just write X as a convex combination of matchings and just take the corresponding. Let's compare each of these MIs. Let's take delta. Delta was the difference between the number of votes that MI wins and N wins. Yeah, Sushmita?
So this representation, decomposition of a fractional matching into integral matchings, is there a basis set or is there any?
Oh, indeed, indeed. So I'm coming to that. Just you're slightly faster than me. Exactly. So let's define it like this. This was like a natural way of defining it. I wanted to say that delta x comma n is just the way, if I write x as summation pi mi, let's just write delta x comma n as summation pi delta mi comma n. And let's say fractional matching is popular if delta x comma n is non-negative for all matches n. However, as Sushmita pointed out, maybe x can be written as a convex combination of many matchings in many ways. It's not unique. So why is this well defined? Why is delta x comma n the way I wrote it? Maybe it can be written as a different convex combination of some other m prime i's, and then it doesn't seem to be a rigorous definition. So let's redefine delta x comma n. In fact, in the way we define it for matchings, let's have an edge weight function, weight subscript x, where x is a fractional matching, where we say the weight of this edge AB under the fractional matching x is just the sum of votes of the endpoints of the edge for each other versus the respective assignments in x. So basically, it's just the sum of these votes, and I've tried to illustrate what A's vote for B versus its assignment in x is. Look at, let's put self loops also so that every vertex is perfectly matched. And so it is just sum of the values it has along edges or neighbors that are strictly worse than B minus the sum of x values it has along edges for neighbors strictly better than B. It is just by linearity. And in fact, what we defined in the previous page, which looked like a natural definition, and this definition, they coincide. So this is joint work with Julian Mestre and Meghna, who is the chair. So in fact, we extended the notion of popularity to fractional matchings in this paper. So both the definitions of delta x comma n are the same. So what looks like a natural definition but may not look rigorous is actually fine, because we could have redefined delta x comma n as, let's just take the sum of votes of all vertices in the manner given here along the edges given by n. So n tilde is just basically, let's just put self loops and so on. So let's just stick with the previous definition because that's more natural, we could say. Either way is fine. So we defined what's a popular fractional matching. It's a fractional matching that never loses an election against any matching. So delta x comma n is non-negative. So let's look at this simple example where there's only one popular matching, that's the blue matching. However, the fractional matching given by half along the value of half along the two blue edges and a value of half along the two red edges, that's also popular. One can check that it does not lose any election. However, the red matching is unpopular. So you can have a convex combination where some unpopular matchings are participating in the convex combination, but the resulting convex combination is popular. So as far as integral matchings are concerned, there's only one popular matching, but fractional matchings we're able to find. So the red matching is able to combine with the blue matching, and somehow they're able to form a popular combination. So how do we describe the convex hull of all popular fractional matchings? It's not integral because there are these fractional matchings that cannot be expressed as convex combination of popular matchings. So we can write it down in the following manner with exponentially many constraints. Delta x comma n is non-negative for all matchings in the given graph. So there are exponentially many constraints, and the remaining constraints such as the matching polytope constraints. So now let's go back to witnesses and show, in fact, there is a much nicer way to formulate this polytope. Rather than these exponentially many constraints, we can come up with, in fact, linearly many constraints, a compact extended formulation. We'll introduce new variables now. And so let's take a fractional matching x. So if X is a popular fractional matching, it's an optimal solution to this LP. So here the variables are the Y sub E's. So X is one particular fixed fractional matching. X is not a variable, Y is the variable here. Let's take the dual LP. So even a popular fractional matching has a witness, that is a dual optimal solution. So, and now let's stick with this dual LP, and instead of fixing this fractional matching X, let's allow X to just move along the matching polytope. So let's make X also a variable here. And that gives us this polytope, which is in fact a compact extended formulation of the popular fractional matching polytope. So this is a much simpler, it has only linearly many constraints. So I just took the dual LP and I also forced that alpha has to be an optimal solution. So summation alpha u is 0. And X is not fixed. It's not a fixed fractional matching. I'm allowing it to be any fractional matching. So the variables here are both X and alpha. And this polytope actually looks quite similar, I would say, to the stable matching polytope, which is a classical object which was formulated many years ago, 30 years ago. So whose constraints are linear. I've just written it as weight subscript X AB is at most 0 for all edges AB, and that weight subscript X of AB is just what I've written below. It looks a little complicated, but just a linear. It's just the sum of votes of A and B for each other versus the respective assignments in X. That's all. And the compact extended formulation of FG of the popular fractional matching polytope is a natural generalization of it, where instead of, if we hard code alphas to be 0, what we get is the stable matching polytope. Instead of saying the weight of every edge has to be at most 0, we're saying the weight of every edge has to be at most sum of alpha values of its endpoints, and sum of all the alpha values across all the vertices has to be 0. So the stable matching polytope is the case where all alpha values are 0. And when you allow this extra degree of freedom, what you get is a popular fractional matching polytope. So we didn't design this popular fractional matching polytope keeping the stable matching polytope in mind, but it has turned out to be a very natural generalization. I just wanted to show that. So by optimizing over the popular fractional matching polytope, we can find a mean cost popular fractional matching in polynomial time. However, it has become maybe difficult to implement, right? We said a student can have 2 advisors, he can be 2 half advisors. But maybe the optimal solution is going to give us solutions like 2 over 17. What does it mean to have an advisor 2 over 17 times or something? So is there a better structure to an optimal popular fractional matching? So we show indeed there is, in fact, a lot of structure. The linear program that led to the compact extended formulation has a very nice property. It is self-dual. That means some nice complementary slackness conditions hold, and that allows us to show this polytope is half integral. So indeed, you will get an optimal solution where a student can have just 2 advisors and each of them is like half an advisor. So let's just quickly see the proof of half integrality. How much time do I have, Meghna?
Yeah, you have 5 minutes.
Okay, then let me finish in 5 minutes then. So let's look at a popular fractional matching X, and let's look at all the fractional values with which it gets assigned to various neighbors. So let's look at the special case when G has a perfect stable matching. In this special case, we'll show that the popular fractional matching polytope is integral. So for any vertex in A, let's arrange all the entries in this fractional allocation in increasing order of A's preference. So X has a witness alpha. I'm using that alpha to split this array into 2 parts. The first part I'm calling of length 1 plus alpha A by 2, I'm calling the blue subarray, and the remaining part I'm calling the red subarray. Now let's swap the blue and red subarrays to get a reordered array. Let's call it X prime. And the order within the blue and red subarrays is preserved. Let's do an analogous transformation for vertices in B as well. So here, the entries are arranged in decreasing order And the initial 1 minus alpha b by 2 fraction will be called the red subarray. The rest of it is called the blue subarray. We swap the red and blue subarrays again. And let's form a table whose rows are these reordered arrays x prime. So x prime arrays for all the vertices are arranged one below another. And let's sweep a vertical line along the table and decompose it into columns as shown here. As soon as you hit a cell wall, freeze. That defines a matching. Again, start moving the line. You hit a cell wall, freeze. That's your second matching. Again, keep moving the line. You hit a cell wall, freeze. That's your third matching. So we get, in fact, it's not clear it's a matching. So we show that, in fact, each of these MIs is a popular matching. So this popular fractional matching can be written as a convex combination of popular matchings, which was not the case in that example we saw. That's because G has a perfect stable matching here. That example, there was no perfect stable matching. So in this special case, in fact, the popular fractional matching polytope is integral when G has a perfect stable matching. And this will imply half integrality in the general case, which means there is always a min-cost popular fractional matching that's half integral. This is joint work with Chin-Chung Hua. And finally, I wanted to use this integrality in the special case to get a result on approximately popular matchings. I'll finish it in 2 minutes. So can we relax popular to approximately popular for the sake of tractability? Popular means no matching wins more votes than this matching. Let's call a matching quasi-popular if no matching wins more than twice as many votes as M. Can a min-cost quasi-popular matching be efficiently computed? Unfortunately, this is also hard. So in fact, both the min-cost popular and quasi-popular matchings are NP-hard to approximate a penny factor. So let's ask for a bicriteria approximation. Can we efficiently find a quasi-popular matching of cost at most that of a min-cost popular matching? And here we finally have a positive answer. So the popular matching polytope and the quasi-popular matching polytope both have near exponential extension complexity. To describe these polytopes, we need exponential size. We're able to show an integral polytope sandwiched between these two that is easy to describe. And optimizing over this leads to that efficient bicriteria algorithm. This is joint work with Yuri Feinzer. So we'll be using this result that if G has a perfect stable matching, then its popular fractional matching polytope is integral. So let's just, in fact, the given graph need not have a perfect stable matching. Let's just augment G with some new edges so that the resulting graph G star has a perfect stable matching. And in fact, the popular matching polytope of G star is easy to describe. That's what we saw in the previous case, because in this special case, the popular fractional matching polytope is the same as popular matching polytope. So,
Can I ask a quick question?
sure.
So if graph G has a perfect stable matching, shouldn't all popular matchings be stable or at least perfect?
Yeah, they're perfect. That's true.
But they need not be stable. That's
They
one.
need not be stable. Exactly.
Given that the stable matching polytope also has a self-duality property, right?
Exactly. So not as exactly as self-duality, but something very close to self-duality. Exactly. But then we could have non-stable perfect matchings also turning out to be popular. So I cannot use that.
That's the case that you're able to capture using
exactly
those
absolutely
things.
So those alpha values are giving that extra freedom in a way. So indeed, yeah. So this is really the last slide. So we are showing that every popular matching can be extended to a perfect popular matching in this augmented graph. So we have the popular matching polytope, that's a red figure. We've in fact, this is a subset of the popular matching polytope in G star. And we show every popular matching in G star when restricted to edges of G is quasi-popular. So that's how we get this sandwich polytope. So that's all I wanted to say. And thank you. So I tried to cover a lot of work today. Sorry if it got a bit heavy. So these are all my collaborators in these papers. And thank you.
Thanks a lot, Kavita. And yeah, you're dot on time.
Oh, thank you.
So I have one follow-up question on what Sushmita asked. So when we are in this case where G has a perfect stable matching, we don't encounter the case that a fractional popular matching is made up of an unpopular matching.
Exactly. So all we are saying is, Meghna, all we are saying is maybe it can be written as a convex combination of unpopular matchings also, but there is also a convex combination using popular matches. Exactly.
So we
you
can
don't
say that Burger-Newman decomposition works for this class of popular.
Exactly. So the popular fractional matching polytope is integral in this case. So any popular fractional matching can be written as a convex combination of popular matchings. So when G has a perfect stable matching, things are very easy.
Not easy, relatively speaking. No, and I wanted to say that we have so many papers and on so many while doing. So you did an amazing job of covering a huge sort of landscape. So thank you.
Thanks. I'm glad you liked it.
I'll ask if anybody in the audience has any question. Okay, so if not, we'll thank once again Kavita for the wonderful sessions to talk.
Thank you.
And
Thank
thanks
you.
to the organizers for arranging this wonderful workshop. Thanks, Sushmita, and thanks, Aritra and Vikram.
Where are my partners in crime?
Okay.
Please say something. I have accepted a lot of thank yous. So now it's your turn. The
So
floor is yours.
thank you, Kavita and Meghna. Thank you for that lovely session. So I've been officially assigned to deliver the vote of thanks, and so everyone is there. So on behalf of the organizers, I would like to first and foremost thank our speakers. All of them readily agreed to give a 2-hour talk on a very short notice, and that made our work really easy. And whatever success that we can attribute to this workshop is because of their engaging and accessible talks. From my own experience, I can say it's not easy to start from basics and reach the frontiers of research within 2 hours. So, and all the speakers did that commendably. So a round of applause to all of you. Yes. And I'd like to thank the chairs, of course, who were informed on an even shorter notice. And they also agreed for moderating the sessions and making them very engaging. So thank you, all of you. Of course, our participants for their lively and active participation in the workshop. And an attentive audience is an asset that all of speakers, they all desire. It's not easy to do that, especially in this online format. So we feel very fortunate to have all of you here. So thank you. Thank you very much for participating. A lot of people have worked behind the scenes. Our volunteer team, they have been sending emails, reminders, following up on speakers and chairs. And besides helping us, the technically challenged faculty. So thank you, all of you. I'd like to especially mention Ananya, Shelly, Sanjay, Shaunak, Shavik, and Shushuvan. You can see them all. They have switched on their videos. So if I miss someone, it is due to my ignorance and not a reflection of their effort. So thank you, all of you. Thank you for helping us. Special thanks to our media team, especially Gayatri. She is the technical person on whose shoulders we left all the responsibility of hosting the Zoom sessions and live streaming on YouTube. It's not that we didn't try, we did try to do it on our own, but we are failing miserably. And it's only when she came on board, we felt very relieved. So thank you, Gayatri, and thank you for being available even beyond the office hours. Thanks a lot. Okay, so and lastly, I'd like to also thank my co-organizers. I'm deeply in gratitude to them, Aritra and Sushmita. I've learned a lot from both of them in organizing such events. And they were the real driving force from day one when we were roped into organizing this workshop, rather beguilingly, by Venkatesh and Saket. So from coming up with suggestions, finding out the topics, what topics to invite people on, and setting up the website, contacting speakers and everything, they were up to the task. So without their effort, I would say this would not have materialized the way it has. Thank you. So Sushmita, Aritra, if you want to add, please feel free to add.
Aritra?
Yeah.
You covered every ground that, much more than I had thought of. So please, more than, I think, Aritra, please, if you want to add some.
Aritra, can you first turn on your camera? Is he on?
Sorry, who?
Okay, yeah.
I'm it's also Sushmita sent a whip that you have to put your camera on. So
yeah.
Yes, so it's much easier in online setting. So I hope that this continues in future years. This is the initial thought of starting this. I in 2019, I talked with Venkatesh and Saket. The initial idea was that there is a sizable algorithm community, and at least once in a year we should sit together and discuss some of the well-known results. So, and I think that this should continue, and hopefully it will continue. And, ideally, this should happen in an offline setting, and I hope that in next year we should be able to do that. So that's all. Over to you, Sushmita.
I really have nothing more to add, given everything that Vikram said. He thanked everybody, and so, I mean, very generously. And Oritra, as he pointed out, that the last year's hiatus, right, it just sort of brought to focus as to how much we were missing out on interacting and learning from each other and so on. So the Zoom, this sort of online platform does have its merits. I mean, I get to attend a lot of talks that I simply wouldn't have been able to travel to and so on. So it's not all bad, but this the interaction that continues with the speakers after the sessions have ended, there is no substitute for that, I think, in this online platform sort of format. So let's hope that next time we are able to, and soon enough, we are all able to gather some of this, all the faces that are here today and some more. And we have an even better celebration of recent trends in algorithms and the roaring algorithmic community, research community that exists in India. So thank you. With that, I'll just end.
Yeah, to Venkatesh for concluding remarks. Yeah.
Also, you covered everything. I think enough people have said everything. Let me also add IMSC for sponsoring this, for honorariums, and we all had a sumptuous lunch on all your behalf today. Thanks for organizing this. So yeah, I think Vikram and Sushmita and Aritra deserve a huge applause for the great work they've done. I think there's a excellent variety of talks, speakers. This whole idea of 2 parts was excellent. I think it went very well. The schedule, finding chairs, international chairs, to make sure that there is some, non-trivial participation for some of these talks. And I think overall everything worked out, and you guys did a great job. And I hope we'll continue again. I think Saket is looking around for hosts for next year. Hopefully you will hear very soon about it. Yeah. So hope to see you all next year again in person. Yeah. Okay. Thank you. Anything else?
No, I think that's
okay. Thanks.
Yeah. Thank you. Thank you.